All right, let's dive right in. Today, we're going to demystify a concept we use constantly, probably without even thinking about it: probability. It's really just the powerful language we've developed to measure uncertainty and, well, make sense of a world that's pretty random. So let's get into it. I mean, we ask this all the time, don't we? What are the odds it's going to rain? What are my odds of winning this game? This simple question is really at the heart of everything we're talking about today. We're going to break down how we can answer it, not with a wild guess, but with a really logical and powerful framework. So first things first, before we can even think about calculating anything, we all need to be speaking the same language. This first section is all about building that shared vocabulary so we can talk about randomness in a clear way. Think of it as the foundation for the whole house. Okay, the starting line for any probability problem is what we call a random experiment. Now, that sounds super technical, but it's not. It's just a fancy term for any process where you don't know the exact outcome ahead of time. You know, like flipping a coin. You know it's going to be heads or tails, but you don't know which one. Same with rolling a die. That uncertainty, that's the key. And to keep things really, really clear, we're going to stick with one simple example through this entire explainer: rolling a single, standard six-sided die. This is going to help us ground all the big, abstract ideas in something we can all easily picture in our heads. So, we have our experiment, rolling the die. The very next question is, well, what could happen? The answer to that is what we call the sample space. It's nothing more than a complete list of every single possible outcome. Everything that could possibly happen, no more, no less. It's our entire universe of possibilities. Yep, exactly. For our die roll, this sample space is just the numbers 1, 2, 3, 4, 5, and 6. That's it. That's the whole list of what could happen when you roll the die. Pretty straightforward, right? Now, most of the time, we aren't interested in all the outcomes at once. We usually care about something more specific. And in probability, we call that specific thing an event. An event is really just a piece of the sample space, a certain outcome or group of outcomes that we want to focus on. It's our target. So for instance, let's say we want to know the chances of rolling an even number. Well, our event, we can just call it A for short, would be the outcomes 2, 4, 6. You see how that's just a smaller selection from our total sample space? That's an event. Okay, we've got the language down. We have experiments, sample spaces, and events. Now we get to the fun part, actually putting a number on that uncertainty. Let's dig into the rules of the game. And the first, most fundamental rule is this one. Probability is always a number somewhere between 0 and 1. Always. 0 means it's absolutely impossible. It cannot happen. 1 means it's a sure thing. It is absolutely certain to happen. And pretty much all of life's interesting maybes fall somewhere on that scale in between. Let's make this super concrete with our die. What's the probability of rolling a 7? Well, it's 0. It's just not in our sample space, so it's an impossible event. On the flip side, what's the probability of rolling a number that's less than 7? That's 1. 100%. Every single possible outcome fits that description, so it's a certain event. Now, this whole system is really built on just 3 simple foundational rules. They have a fancy name, the axioms of probability, but don't let that fool you. They are so intuitive. Honestly, it's just common sense written down. And here they are. First, a probability can never be negative, right? Makes perfect sense. You can't have less than a 0% chance of something happening. Second, something has to happen. The probability that one of the outcomes in our sample space occurs is 1. And third, if 2 events can't happen at the same time, like rolling a 1 and a 6 on the very same roll, the probability of getting one or the other is just what you get when you add their individual probabilities together. That's it. That's the whole foundation. So we have our rules, but what happens when this situation changes? This is a huge idea in probability. It's not static. The odds can actually shift as you get new information. And this is where things get really, really interesting. So let's think about this. With our die, the numbers less than 4 are 1, 2, 3. That's 3 possibilities out of 6 total. But what happens to those odds if I give you a little clue? What if I lean over and tell you, hey, the result is definitely an odd number? Does that change how you'd calculate the chances? It absolutely does. And this gets us to the idea of conditional probability. It's the probability of something happening given that you already know something else is true. The key insight is right there on the screen. New information literally shrinks your sample space. It lets you cross off possibilities that you now know are impossible. And this just shows it perfectly. Before the clue, our whole world was those 6 numbers. The odds of rolling less than 4 were 3 out of 6, which is 1/2. But as soon as I told you the roll was odd, our universe of possibilities just shrank to 1, 3, and 5. And in that new, smaller world, the outcomes that are less than 4 are 1, 3. So the probability actually jumped from 1/2 all the way up to 2/3. That is conditional probability in action. So, we've covered the language, the rules, and how new information completely changes the game. These are the absolute fundamentals, the building blocks that open up the door to some incredibly powerful ways of thinking. Let's just take a quick peek at where this road leads. So, the total opposite of conditional probability is this idea of independent events. And these are pretty much what they sound like. Events that have absolutely nothing to do with each other. The outcome of one has zero, zilch, no impact on the probability of the other one. And the classic example here is flipping a coin. If you get heads on the first flip, does that change the probability of getting heads on the second flip? Nope, not at all. It's still 50-50. The coin doesn't have a memory. The two events are totally independent of one another. So you've got events that depend on new information, and you've got events that don't. The crucial idea is that we can use this logic of conditional probability, this math of how information changes the odds, to build a whole system for learning. And that brings us to one of the most famous and influential ideas in all of science, Bayes' theorem. And really, at its core, this is what it's all about. Bayes' theorem gives us a formal recipe for doing exactly what we did with our die a minute ago. We started with a belief, the odds of rolling less than 4. Then we got new evidence. The roll was odd. The theorem is just the math that shows us how to perfectly combine those two things to arrive at a new, updated, smarter belief. It's like the mathematical engine for learning from experience. So we'll end on this thought. Probability doesn't get rid of uncertainty. That's just part of life. But what it does give us is this incredible toolkit to manage it, to measure it, and ultimately to make smarter choices because of it. It teaches us how to think clearly about what we know, what we don't, and most importantly, how to change our minds as we learn more. Thanks for watching.